power of 2. So I'm giving you like some hints to understand how it works. Okay, so have you thought about the number? Okay, so and you have to tell me if the number is in the class or not. Okay, in the class there are 8 numbers in each of them. Okay, you need to focus on the class and later you can play with the class or you can see the numbers. Okay, so is your number here? Sorry, you can write one. So you have to tell me yes or no. There are 7 cards, and you can write one. Or you can make one. You can is your number here? I thought you that this is super difficult. So you tell me. Okay, so you first go. And you can do the first question. No, okay. So time is 1, July is time, and then the number is 12. Well, it could work because it's a math thing, not a magic thing. Okay, so I just confused at some point, but okay. So this is like your homework, and you make some work, and then you can do the trick to me. Yeah, it's so complicated. But the idea, what was the number? 13. Oh, I forgot to add that. So, the idea is that the yes and the no are like in binary, so the digits of the number that you are thinking. So, the first, but you have to send it later. You have the call, you can show to the other, and then you try. So, the idea is that the first 4 cards are the digits of the number in binary. And with the other circle, you say it was theory. Did you remember that was the Hamilton? So, the last 3 digits was the information, like for checking right and left. And with this code, you can convert into one. But I detected that there was a little by this. Okay, so now I want to do again, because we have to find the last thing that we do, we have to find the parameters to compare it. So you find the length, the dimension, the distance. All of that? But what is here? This is the M1, M2, M3, M4, R1, R2, R3. So what I was trying to do was to enumerate all the words in the code, okay? So I started by taking like 4 zeros, and then I compute the other 3 bits. Do you remember that the first one is actually the addition of these 3 ones, this one is the addition of this one and these 2, and the last one is the addition of these 2 ones and this one. Okay? So I'm going to enumerate all the words of the code. So you're going to have like 16 words. My representation of the numbers from 0 to 100. So the idea is that here I'm writing like this is 0, 1, 2, 3. And then you can compute here which are the values for the R1, R2, and R3 for the rest. Okay? By the way, the notes for this one are online on the website of the CIMPA School. So actually you have the lecture of yesterday and today. Actually there you have like 4 days. And you also have the exercise. But I mean, imagine that you write all of them. Of the code. I recall that the weight of the code is the smallest weight of a non-zero word. Okay? So if you look at all of them, actually you can check that the minimum weight is equal to 3. That, for instance, it is attained by this word. Okay? The first one is everything 0, so you don't count it. Okay? So you get that the minimal weight is equal to 3. This implies, as we said, that was the last proposition that we proved yesterday, that for a linear code, and this is a linear code, the minimal weight is equal to the minimum distance. Okay? So basically, this is equal to V. We already knew that for this code, the length n is equal to 7, and that the dimension is equal to 4. Do you remember why? Because, I mean, actually we have, if you want, like, 4 degrees of liberty. So for M1, M2, M3, and M4, you can choose whatever you want, and then the other 3 are determined by this 4. Okay? So, I mean, this also tells you that the cardinality of the code is 2 to the 4, because here the alphabet, Q, was equal to F2. So it had 2 elements. It's hard to write down here. So it has 2 elements. So basically, I mean, the important parameters of a code, or the main parameters, if you want, are the length, the dimension, and the minimal distance. Okay? So in this case, you can use the notation. You can write that this Hamming code is actually what we call a 7, 4, 3 sub 2 code. So again, that means the length. So with this information, we can construct something like for the word polynomial. Okay. And this is defined as a polynomial in two variables, x and y. Then it is done this one. So I'm just going to do a value. If you look at this polynomial, if you have a regular polynomial, okay, in two variables, x and y, we're looking at all of the calculation of the and also to find these values. This value actually can be found as the number of the You can find the book. I'm not going to read it right now. It's a little bit out of the scope of this course. It's a little bit technical. It's with the unity and character. But you can find it in the reference book. Yes. Yeah, you cannot have, thank you. You cannot have grade 8 because I mean they are worth of 11, 7, so it's more. You can have grade 7. Yeah, thank you very much. Sorry. Okay, so I was saying that the proof, I mean, it's a little bit out of the scope of this course. If you are curious, you can look at it at the book. Okay, the only thing that we are going to do actually is checking the quality for some codes. So this is an exercise. So you will find it in the note, the exercise, and tomorrow we can discuss about the exercises, okay? Okay, so before we move to another thing, I'm just going to say like some last things about this problem. So we were talking about the distance. Here we got distance equal to 3, and I'm going to do again the picture that I did yesterday. The idea here is that if you have two code words, so 2 points in the code, then the distance is greater or equal than 3, okay? That means that you can correct up to 1 error, again. Why? Because if you only have 1 error, then you are getting a point that is like, this is radius equal to 1. I'm going to write here another radius equal to 1. So basically, I mean, for each code word, I can consider the ball of radius 1 that I defined yesterday. And because the minimum distance is 3, those balls, they don't intersect. Right? So now what I can do for correcting, this is the idea, if I get something that is here, for instance, that is something with 1 error, I can decode. And I can assume, well, I know if there is at most 1 error, that if I got a word here, is because I had this word. Okay? This is again the motivation of the distance. So, yeah, in this case, this is why we can correct 1 error, because the minimum distance is 3. So, I mean, in general, with this argument, what we have is that the minimum distance, if the minimum distance is equal to d, then you can correct up to d minus 1 divided by 2, the integer part. You know the meaning of that, right? I mean, this is a maximum integer that is smaller or equal than d minus 1 divided by 2. Because in this way, if the minimal distance is d, like here that is 3, you can construct the balls of radius d minus 1 divided by 2. Okay?
So from the Hamming's point of view of the coding theory, actually this is what we want. At the end, what we want is to be able to construct codes that, given a length n, the dimension is very big and the distance, the minimum distance, is also very big. Of course, you cannot have these two things at the same time, but if you fix n and k, you can wonder which one is the code with the biggest minimum distance. Because the biggest minimum distance is going to give you the maximum number of errors that you can correct. Okay? So again, to fix ideas, Hamming point of view is this one. You want to construct good codes, and then with the good codes, you also want like a good encodings and good decoding. Okay? That means a little bit so decoding is like given the representation of the code. So this we're going to discuss now about generator matrix and different ways of doing it. And the decoding is like the problem that was here, that if I have, for instance, a point here, how do I recover the word that is in the code that is closest to this one? So this is difficult, and you know because I failed to do it, even if I had a system, but well. So Hamming, what we want is to find like good systems for this decoding, okay? And as I said, actually, this is a difficult problem, the decoding in general. And this is why it's good for crypto. So I'm just going to state the theorem that is by Berlekamp, Michaelis, Van Tilburg, from the 88, that state that actually is a difficult problem to find, formalize the meaning of what is a difficult problem, to find the closest, like if I give you a point, find us the closest code word, okay? So, the following problem is MP complete. So MP, for the ones that doesn't know what it means very difficult, okay? So let's see via code write an element in the full vector space FQ to the n, and T a natural number in this set. Decide if there exists an element in the code such that the distance of y to c is smaller or equal than t. So this is not even giving the word that is closest, it's even deciding if there exists a word that is close enough. So this problem, in general, is difficult. This is the meaning of this theorem, okay? It's like in general. So basically, it's like giving a general algorithm for decoding a code in here. This is the meaning of finding like the closest vector with some restrictions. This is a difficult problem. So there are some particular codes for which you have a decoding algorithm that is good, as the one that I was trying to solve. Okay? But in general, if you want an algorithm that works always, there is no way. And of course, this is a problem that somehow has a solution, right? Because the solution, it could be, okay, I take like all the words, and I compute the distance for all the words to decode to y, and I check if one of them is smaller or equal than t. So actually, you have a solution for this problem. The solution is very expensive. You don't want to do that. In the moment that Q and N is very big, you are not going to do that. The complexity is super high, okay? But again, this is why this is going to be good for cryptography. So for my last lecture, actually, we are going to study a crypto system due by Michaelis that is based in the fact that this is a difficult problem, okay? Okay, so this is for another day. Now I continue. So I'm going more now with the encoding. How do we represent a code? Because, I mean, at the end, a code is just a subset of FQN. So, I mean, I'm going to focus again on linear codes. That was one question yesterday. Why linear codes? Well, because they are easy to describe, let's say. This is one of the advantages, okay? So how can I describe a linear code? By a basis, because it's just a vector space, right? So let C be an NK linear code over FQ. Okay? We can get a basis. Let G1 until Gk a basis. So why there are k elements in the basis? Because the dimension is k. Okay? And now each of the Gi here, they are vectors that they are in FQ to the n. So they have n coordinates. Okay? So we call a generator matrix for the code is just a matrix G that is made up of those vectors of the basis. So basically, I just write like this. The vectors. So, okay. Okay? If you want it in an extended version, here you have the first coordinate of G1 until you have the last coordinate, Gyn, Gk1 and Gkn. So it's a matrix. Here the side is n, and here the side is k. Okay? This matrix is not unique. Okay, so you can give different generator matrices of a code. Because at the end, this matrix depends on the choice of a basis. So, I mean, an easy thing that you can do is, for instance, permuting two elements of the basis. So you are going to get a matrix with two rows that they are permutated. Or even, you can just take any other different basis. Okay, so this is not unique. Examples. So we can take, so far we haven't seen like so many codes, so I'm going to get like an easy examples. Imagine that you get this code, the trivial one. So you only have 0. So who is in this case the generator matrix? The empty matrix, yes, 0. I mean, here you don't have a basis. Okay, so maybe it's not a very good example. Okay, let's take another trivial code, this one. So the total space. Who is a generator matrix here? The identity. I mean, you just need something that generates everything. So I can, for instance, take the canonical basis here, and then when I put the canonical basis like this, for creating the generator matrix, what I get is identity. Okay? Well, for this we said nothing, and for this we got the identity matrix of side n. Okay? Now I'm going to give you the generator matrix for the Hamming code. Okay? Maybe I'm going to get this. So what do I need for getting a generator matrix for the Hamming weight? So I know that it's a code of dimension 4, right? So if it's a code of dimension 4, I need 4 linearly independent vectors, right? So an easy way of getting those vectors, because of the way I construct it, actually is I can get the 0, 0, 1, blah, 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 the 0, 0, 1, 0, blah, 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 the 0, 1, 0, 0, blah, blah, blah. And in this way, I ensure that the 4 vectors I'm taking, they are linearly independent. Okay? The problem is that now it's wet. I think I cannot write it here. Well, I'll erase the other blackboard, and then I come back. So, well, the idea after this is that, as we said, the generator matrix is not unique. But we can find a way, well, we can add some conditions to get kind of a canonical generator matrix, let's say. So this is going to be related, I mean, I guess that you know, like Gauss elimination. So when you have a system of equations or some vectors like this in the basis, you can play with them for normalizing and getting what is called an echelon matrix. Okay. Almost done. Perfect. Okay, so for the Hamming code, what we get is this matrix. So, I mean, as I said, I just took 4 linearly independent vectors. So those ones generate all the code, all the subvector space, okay? And moreover, I did it more or less in a clever way, because, I mean, this matrix, it has a special shape, okay? It's what is called a reduced row echelon form. Okay? So what is the idea? How did you get that? I mean, this is just Gauss elimination. You start with any generator matrix of the code. Okay? You look for a vector, for a row in which you have a non-zero element. Okay? You put that row at the beginning. Now you multiply by an appropriate number in order to get a 1 here. Okay? Now that the first row here has a 1 in the first position, you subtract as many times as needed this first row in order to make zeros here. Okay? And now you repeat the operations with the other columns. And in this way you get what is called the pivot. Okay? The elements that they are here. Once that you get something like this, what do? You use these vectors to make zeros also over here, if needed. So in this way, you get here something that is like in the echelon form and only with ones. Okay? Maybe you don't get necessarily like a diagonal matrix like here in this part, because maybe you can get like some extra zeros. These things can be moved left. But it's not a problem. And the funny thing is that, I mean, after doing this Gauss elimination, in order to get like this shape in the matrix, this matrix is unique. So for instance, you can compare 2 codes by computing these 2 matrices and checking if you get the same one. Okay? And actually, this shape of the matrix is going to be useful for computing something later that I'm going to describe now. Okay? Because somehow I told you this is a way of describing a code that is by the generator matrix, so I give you a basis. But if I want to describe a subvector space, there is another way of doing it. Which one? By equations. I mean, when you have a vector space, you can give it in an explicit form, this is by a basis, or you can give it in an implicit form, that is by equations. The equations that they are satisfied by all the vectors in the vector space. Okay? So this is another definition. So we start again with C, FQ, linear NK code. And we take H, a matrix, M times N. I'm going to say who is M later. matrix with entries in FQ again, okay, and such that C is actually the kernel of the matrix. Okay? So somehow if you want, the rows of 8 are the equations that are satisfied by C. Okay? So I can rewrite this in another way. So C is the set of all C in here such that 8CT is equal to 0. I wrote the transpose because for me, I think that it was clear when I wrote it there, vectors are like this. So are 1 times n matrices. Okay, so if I want to do the product like this, I want a column vector, so I have to transpose it. Okay? So in this way, 1/8 like this is called, 8 is called parity check equations matrix. So what can we say about M? So if you want N, 8 is an M times N matrix, okay? Because I'm multiplying like this. So, and the side of this vector is N. So this is why I need the N here. And the M actually is the number of equations, okay? So because of the dimension of the code is K, what we have is that K has to be greater or equal than N minus M, okay? Greater or, we get the equality if the M equations that I'm getting are linearly independent. But it may happen that I'm getting like extra equations. So this is why we have an equality. Okay? Now, if I get such a matrix 8 where the equality holds, that is where M is equal to N minus K, okay, then we say that 8, I started wrong. Then 8 is called a parity check matrix. Okay? So basically, you are just taking the equations that you need for defining your vector subspace. Okay? Again, this matrix is not unique. Okay? It depends. You can get like a different combination of the equations and still getting a parity check matrix. Okay, so maybe this is a little bit confusing, so I'm going to make an example. So imagine that over F3, you consider the code that is generated by this matrix. 1, 0, 1, 2, 0, 1, 2, 1. Okay? So I'm taking this code. You see, now it's easy. Now that I introduced the formalization of the generator matrix, now it's super easy to describe a code. You just have to take a matrix. Okay? So let's take this code. So this code is defined over F3. Okay? Who is N? We can read it from the matrix. N is this length. So N is equal to 4. And who is K? K is the dimension of the code. So it's the number of elements in the base. So this is K equal to 2. Okay? So I took the generator matrix already in this special form. Okay? This reduced row echelon form. And you're going to see why this is useful. Because what I want to do now is from this G, I want to construct an 8. Okay? So this is linear algebra. This is supposed to be easy. Okay? But I mean, I'll show you that when the matrix is written in this form, it's especially easy. Okay? So we need to construct this 8. How does it look like? So we know that 8 has to be an n minus k times n matrix. Okay? So you are going to get, let me write it like this, so it's going to be clear. Here I need n, and here I need n minus k. Okay? So with my parameters, n is equal to 4, and n minus k is equal to 2. Okay? And what I need to write down here basically are equations such that this vector times this one is equal to 0, and times this one is equal to 0, and then the same thing with this. Okay? So what is my idea here? My idea is that you take first here a square of psi n minus k times n minus k. Okay? And I write here a matrix with determinant different from 0. Whatever, but determinant different from 0. So basically what I want is n minus k vectors that they are linearly independent. An easy choice for this is the identity. So in my case, I get this thing. Okay? And now what I do is like I complete here to get the condition that this is equal to 0, this is equal to 0, this is equal to 0, and this is equal to 0. Okay? But now it's easy. Why? Because I also have the identity here. So basically, for getting the first number here, this is going to be multiplied by 0. So it doesn't matter for this vector what I write here. And the same thing for the other ones. So basically, the choice that I do here is only useful for killing the first one. Okay? So I compute, this is 1. So basically, I need a 2 here. Because then it's going to be 2 plus 0 plus 1 plus 0 equal to 0. Okay? For getting the element here, I'm going to multiply by this one. So you get 0 plus something plus 2 plus 0. So I need a 1. So I get the row that I need. I mean, you can do it as you want. This is linear algebra. So I mean, I'm just looking for a matrix because I mean, I see faces like, what are you doing? So maybe you have another strategy. So if you have another strategy, go ahead. I'm just showing a method of doing it. Okay? And again, for the last one, you want this thing to be 0 and this thing to be 0. So here you have a 2. So here you need a 1. And for this one, you get 0 plus something plus 0 plus 1 equal to 0. So you need a 2. Okay? So in this way, I got a Parity matrix. Okay? So the code I was considering, you can describe it in 2 ways. Or well, giving a basis like in here, or giving like the equations of the code. Okay? So the rows of this matrix are the equations. Okay? So, I mean, if you want to formalize this a little bit, what you have is like 8 times g is equal to 0. Why? Because you have that 8 times any vector of the code is equal to 0. So in particular, well, I mean the transpose. In particular, 8 times the generator matrix that is made up of vectors of the code is equal to 0. Okay? And even more, I mean, in this thing, I can get the transpose in both sides. So this is 0, again, if I do the transpose. And what I get here is g times 8p. So here you can see kind of a symmetry. If 8 were the generator matrix, then G would be the parity check matrix for 8. Okay? This we're going to use it later. Okay. Very good. So, okay, why this parity check matrix is also useful? It is useful because it's going to help us to compute the minimum distance of a code. Okay? So far, for computing the minimal distance, what do we do? We took the Hamming code, and basically we have to break down all the words, computing the weights, and checking. So, I mean, of course, this is not very efficient. We agree, right? So now we're going to see how we can compute this minimum distance just by looking at the parity check matrix. Okay? So for this, we are going to prove the following theorem. So what time I've been speaking like for 30 minutes. 35, and a little bit lost with the time. Well, we are fine. If at some point I'm speaking so much, you tell me to stop. So theorem D that is the minimum distance is equal to the smallest integer d such that the columns of 8 are linearly dependent. So we're going to prove this. Okay, if you want, we can do an example, but here, with this example that we have here to compute the minimum distance. So the idea is like, is the smallest integer d such that the columns of 8 are linearly independent? Okay, let's check. If I take d equal to 1, all columns are linearly independent. Because, I mean, I don't have a column that is 0, 0, right? So the condition is not satisfied. So I try with the next one, d equal to 2. Okay, do I have here 2 columns that they are linearly dependent? No. I mean, the 4 of them, they are linearly dependent. But if I only take 2, I don't have one that is a multiple of the other. So I keep going. So now I get d equal to, so there is a minus at some point. Yeah, well, there is a minus here, actually. Well, now 3. Yeah, if I take 3, they are linearly dependent. Okay? So this would imply, and this is why I'm saying that actually here is a plus. Sorry, I forgot. We are going to see it in the proof. Okay? So basically, we found 3 linearly dependent equations. So d equal to 3 is the smallest integer for which there are 3 linearly dependent equations. Okay? So this implies that in this case, d is equal to 2. Okay? Now we're going to prove the theorem. Okay? This is important thing. But what is nice here is that actually you can check, if you want to play, you can try to compute all the words in this code. And indeed, checking that the distance is equal to 2. Okay? How many words does this code have? So the dimension is 2, and it's over F3, so 3 times 3 equal to 9. There are 9 words in this code. Okay? Okay, let's prove the theorem. Okay, so we start with some notation. So we write the matrix 8 like this, with columns. Okay? So they are key columns. We take C, an element of the code. We call W the weight of the word. Okay? And we take the support of this word. So we number it like this. So let me explain. I wrote, but I explain. So I take any word, okay, in the code. Let's say that the weight is W. Okay? So the support of C are the indexes of the coordinates that they are different from 0 in my word. Okay? So they are W of them because the weight is W. Okay? So I number them by G1 until GW. Okay? So what I get, because C is a parity check matrix, okay, that this is equal to 0. Okay? So in particular, what I get is that this is equal to 0. So basically this code word is telling me that those columns, they are linearly dependent. Okay? Because these numbers, they are different from 0. So I found a linear combination that is non-trivial of these vectors that is equal to 0. Okay? Then these guys are linearly dependent. So what does this imply? This implies that if I have a column, an element of weight W, well, different from 0, of course, okay? Then I can find W linearly dependent columns. Okay? So this implies that the minimum weight that is smaller or equal than this is smaller or equal than this number of linearly dependent columns. Okay? So now we have to prove the reverse. Okay? So for the reverse, oh, you cannot see if I write here. Sorry. Yeah, sure. W is greater or equal than D. We because there is a smaller. Yes, you are right. Thank you. Yeah, totally right. Thank you. I was thinking D minus 1. My time is over? Oh, okay. Can I finish the proof? It's 2 lines? Thank you. But I started a bit late. Okay. I was erasing. Sorry. Okay, so it's really 2 lines. Don't worry, I'm not going to take so much time. So conversely, if you have HG1, HGW linearly dependent, okay, then there exists a GI, not all, well, in FQ, and not all equal to 0, such that the sum is equal to 0, right? I mean, this is the definition of linearly dependent, okay? Now, what I'm doing is I'm going to define a vector C in FQ to the n such that its coordinate is equal to 0 if I is different from one of these indices. So yeah, let me call it CL. And it's going to be equal to AGI if L is equal to GI. So basically, I extended this thing to be a word in FQN, okay? But then, we have that this thing is equal to 0 by construction of this vector, which means, by definition of the parity check matrix, that C is an element of the code. But what is the weight of the code of this word? W, that is the number of coordinates that they are different from 0. So basically, if you are able to find D linearly dependent columns, then you are able to find a word that has weight equal to D. So that gives you the other inequality. And then you've proved the theorem. Okay? So if I went a little bit fast here at the end, again, you have the notes in the website. So you can reread and check again. And if you have questions, of course, you can ask me. Okay? Even if you have questions now, you can ask. Okay, thank you.